Hi, Science 20s. Mr. Riley here, and I'm wearing my trusty helmet because we're going to talk about how the idea of impulse can be used to explain how safety equipment works. And impulse can also be used to help us design better safety equipment. So, um, first thing I want to do is we're going to take a look at this formula here. This tells us that the impulse or the change in momentum is equal to the force applied multiplied by the amount of time over which that force is applied for. Now, I think for this context for safety, it's going to be a little easier to, it's going to help us a little bit more if we manipulate this formula. So I'm going to change this formula into force is equal to the impulse divided by the time. Now, so the idea here, when we're talking about safety, is that in order to reduce the amount of force, we have to try and manipulate something on the other side of that formula in order to allow us to reduce the force. The force that I'm going to feel as impact, my head's going to feel when it hits something, is related to my change in momentum. So I'm going to have a momentum and I'm going to hit something, and then my momentum is going to be really zero. And I want to actually increase the time over which the momentum of my head goes from a high momentum to a low momentum or to zero. And so basically what I have to do is I have to implement some way to slow down or increase the time over which my momentum slows down or stops. Okay, so I'm going to show you guys an example here. So here is a famous hockey player, Craig McTavish. He was the last player in the NHL to not wear a helmet while he was playing. So I'll take you through this problem here. We're going to use hockey helmet as our example. So a 70-kilogram hockey player with no helmet falls headfirst to the ice at 6 meters per second. The impact lasts 0.1 seconds. So his head falls to the ice. The impact where it hits the ice takes 0.1 seconds. So it takes 0.1 seconds for his head to slow down from 6 meters per second to 0 meters per second to stop. What is the force applied to the player's head? So we can use this formula to help us answer that question. But in order to use that formula, we're going to need to calculate the impulse or the change in momentum. So I have here some information that we're going to need. So the mass of this player is 70 kilograms. The initial velocity, I said in the problem, was 6.0 meters per second. The final velocity, we have to assume this number is going to be 0 meters per second, right? His head's going to hit the ice and it's going to stop. And the time over which that collision happens is 0.1 seconds, really fast. So let's find the initial and the final momentum so that we can find delta P, or we can find the impulse. So my P initial, my initial momentum, is going to be my mass multiplied by my initial velocity. So that's going to be my 70 kilograms multiplied by 6.0 meters per second. So that's going to give us 70 times 6 is 420 kilogram meters per second. So that's how much momentum the player has as he's falling towards the ice. Now my P final is, well, we'll calculate it, but I think we know what it's going to be. If he has zero velocity, his momentum is going to be zero. So it's 70 kilograms multiplied by 0 meters per second. So it's going to be 0 kilogram meters per second. So that's going to be my P final. Now to find my impulse, one of the ways I can do that is P final minus P initial. So it's actually going to be 0 kilogram meters per second, subtract 420 kilogram meters per second. So my delta P is going to be equal to negative 420 kilogram meters per second. So that's my impulse. That's my change in momentum. A player goes from a high momentum to a low momentum. It's going to have a negative impulse. And so now we can take that and we can go back up to our original formula. So to find the force, we're going to take our delta P, which is negative 420 kilogram meters per second, and we're going to divide that by our delta T, which is the time of the impact, 0.1 seconds. Now, when we do that, we're going to take negative 420 divided by 0.1. So what that's actually going to be is negative 4,200 kilogram meter per second squared, and the other name for that is newtons. So this player is going to feel 4,200 newtons of force when he hits the ice. That's a lot. Okay, now let's take a look at a player. Oh, look, it's Connor McDavid, a player with a helmet. So this is a player of the same mass, falling at the same speed, but because that player is wearing a helmet, the impact lasts longer. We are increasing the time, which means hopefully we're going to decrease the force, and mathematically we're going to take a look at how that works. So the only thing different here is my time. Okay, so the momentum of the player is the same. Okay, and so when we do our formula up here, we're going to take that delta P, negative 420 kilogram meters per second, but now we're going to be dividing that by 1 second. So 420 divided by 1 is 420. So negative 420 kilogram meters per second squared, or negative 420 newtons. So when we look at Craig McTavish with no helmet, he is going to be feeling that much force against his head. When we look at Connor McDavid, who is wearing a helmet, he's going to be feeling only 420 newtons, which is 10 times less. So the point of the cushioning that's in the helmet is to slow down the impulse so that we can decrease the force. If you increase